Good morning, everyone, and thank you for joining us in our second part of the Informs MIF 2024 Summer Webinar Competition. For today, we're going to have another set of 5 different speakers. We'll start with Prabhat Hedge, who's a PhD candidate at the Thayer School of Engineering at Dartmouth College. Then we'll have Megan Meredith, a fourth-year PhD student at the Georgia Institute of Technology in the Stewart School of Industrial and Systems Engineering. Then we'll have Sekai Wang, who earned his PhD in Industrial and Systems Engineering from the University of Tennessee, Knoxville, just this summer. And Yanan Xu, who is a third-year PhD candidate in Operations Management at the University of Maryland. And then we'll finalize with Shihan Shang, who's a third-year PhD student at the Industrial Systems Engineering School at the Georgia Institute of Technology. And I want to invite all of you, including our speakers, you're also welcome to vote here, scanning this QR code. I'm going to be sharing this in a link a little bit later. Remember that each of you is going to have a total of 11 minutes to make your presentations, including addressing the Q&A section. And so with that, I pass the baton to Pratat. I think you can get started now.
Thank you so much for that introduction, Sophia. Let me quickly get started in presenter mode. I hope everyone can see my screen. Good morning, everyone. I'm going to be talking about my research on rural school bus routing and scheduling. This is work in collaboration with my advisor, Dr. Vikrant Vaze. So brief motivation as to why this research is important. On a daily basis, roughly 25 million students take the school bus to school. That is actually 55% of all school-going kids. And when you actually look at that number put together, it actually would be the largest single public transportation fleet in the US, more than transit, airlines, buses put together. And despite this massive amount of transportation, academic literature has hardly focused on this topic. So to the top right, there is a figure of the number of papers that have been published on this subject since school bus routing was studied as a problem in OR. And you can see that only in the last decade, people really started looking at this subject more seriously. And most of the literature caters to urban environments, and very few papers actually look at rural school bus routing. And most existing studies focus on minimizing number of buses or vehicle miles traveled. And I will touch upon why our approach, which is different, is kind of important, specifically in the rural context. So to contrast an urban service environment or a suburban service environment with a rural one, I take the example of Cambridge, Massachusetts. And I contrast this with Hanover, New Hampshire, where Dartmouth's located, and it's our partner school district. So you'll see that service areas in rural school districts are typically larger, and thus the rural school bus routes tend to be much longer than urban school bus routes. Point number one. Point number two is rural school bus fleets tend to be much smaller than urban school bus fleets. And rural school bus fleets are also characterized by what we call mixed loading. By that, for example, if you look at the image on the right, on a single bus route, you have students from multiple schools sharing the same ride, whereas in urban or suburban school districts, you typically have students from a single school sharing the ride, and a trip is completed, and the next trip caters to a different school. And in an urban school district or a suburban school district, buses are typically well utilized, and they're often complemented by public transit. However, in a rural school environment, bus capacities are seldom met, and private commutes are the only other alternative. And the other key feature of rural school districts is they've gone through something called rural consolidation. So typically, rural schools have fewer number of schools, and they're clustered together pretty closely in distance, and there are few alternatives to commute between these schools. Here, when I contrast Cambridge with Hanover, New Hampshire, you will see that there's only one primary road connecting the two different clusters of schools, if you will. So in summary, we wanted to see, hey, we looked at Hanover, but is this generalizable to many other school districts? So when we look at our vicinity in Vermont and New Hampshire, we see that most school districts are rural in nature, and the average travel time between the schools is considerably less. As you can see, that most of the map is filled with this yellow color, and most school districts have fewer than 5 schools. So these are features that are generalizable across many school districts. So in order to determine what our objective function should be, we surveyed parents of school-going kids in our school district, and we found that the decision of whether or not a child takes the school bus is the detrimental factor for that determination is the duration of the school bus journey, both from parents that regularly send their kids to school via school bus and students whose parents drive them to school on a regular basis. And then I briefly mentioned the congestion, that there are fewer alternatives. So we ran an experiment of looking at the number of vehicles passing in front of the 3 schools that we have in our school district on a week when the school was closed, and the next week on the same day of the week when the school was open. And all things equal, we have evidence to say that there are roughly about 160 cars more in the 15 minutes prior to when the school starts at around 8 a.m. So congestion is also a big issue in rural school districts. So major contributions of our research to address this problem, we formulate a mixed loading, fixed number of buses, mixed integer program to minimize student travel time. Our model is actually unique in the school bus routing literature because it combines multiple subproblems of the school bus routing problem, as is in the literature. Our model is able to select bus stops, design routes, create a time schedule for the buses, and handle different school start times. Our model, however, in entirety is complicated to solve. So we have a heuristic that deploys a relaxed version of our formulation in a road network-aware cluster than route heuristic. By that, I mean when you cluster in urban areas, the road network is regular. Clustering in rural school districts is not that straightforward. So we have a improvement integer program that uses the structure of the road network to improve initial solutions. And then we combine our routing heuristic with a demand congestion equilibrium to address the lower utilization rate and reduce congestion in the vicinity of the school. Just to give you a flavor of our model, our full model has an objective function and about 50 constraints. It will be out in our preprint pretty soon. But our model is an arc-based formulation where we have a set of nodes representing school buses, set of nodes representing bus stops, set of nodes representing schools, and then there are arcs connecting these different types of nodes. And our objective function is to minimize student travel time on the bus. And then we have a few constraints. I will go through them briefly. So we have binary variables that determine whether or not a bus travels between 2 nodes, and whether RIK is a binary variable that looks at whether or not a bus stops at a given stop. And we have some other constraints that look at the continuity in time and when a bus reaches a given stop or not. And then we have some constraints. This one's a nonlinear constraint, but we use a linearized version in our actual model, where we say the time count for a student on the bus starts only after the student's picked up. And we have similar other constraints in our full model. You can read this in our preprint, which will be out pretty soon. So that is the routing part of our solution methodology. So what do we actually do? We use a clustered route heuristic in the first stage where we solve a relaxed version of our integer program on a given cluster and then improve those initial routes using some improvement heuristics. And in the second part, we look at the impact of the improved routing on the decision of whether or not a student takes the school bus to school, and look at the impact of congestion in the vicinity of the school based on this new route. And we iteratively solve the heuristic and the demand congestion equilibrium until we can no longer accommodate additional students, or we cannot improve time without having additional students. So we deploy this methodology on 2 school districts that are very similar in nature, roughly about 500 students in both cases, give or take. And the school start time is the same in these 2 school districts. And what we end up finding with our methodology, just with the routing heuristic, is that we're able to generate a 17.34% improvement in the school district of Hanover and about a 15.33% improvement in the school district of Hopkinton. And just to give you an idea, to the right is one of the results for a single school. We have this repeated for the 3 schools in both the districts, is an improvement in student travel time compared to the existing routes that the school district currently deploys. And you can see, except in the vicinity of the school, in most of the map, you have a considerable improvement in using our solution methodology compared to the baseline methodology. So that is the routing part. So what do we end up doing with the iterative part to help congestion? So Hanover has about 1,200 students, and through the survey, we assume that 40% of the students always take the bus in blue, 20% of the students take the bus sometimes, and 40% of the students never take the bus. And in the vicinity of the school, we assume that congestion builds up in these areas. And then everywhere else, backed up by congestion, there's speed floor equations that determine the speed of travel in those road segments. And what ends up happening when we apply our iterative heuristic is that we start with students that take the bus regularly or always take the bus, which is 540 students with an average student travel time of 24 minutes. And as we iteratively improve the routes, we're able to handle 660 students and reduce the student travel time at the same time by 5 minutes using our iterative improvement. With that, I'd like to end my presentation. Thank you so much for your attention.
Thank you, Prabhat, for your presentation. We unfortunately do not have more time for questions. If we have time at the end, we can do that. Or if anyone wants to ask in the chat, that's a possibility as well. So I would like to welcome now Megan Meredith.
Thank you. Let me share my slides. Okay, thank you so much for the introduction and for organizing this. So today I'm going to discuss my research that's in collaboration with my advisor, Dr. Lauren Steinley, looking at the implications of using maternity care deserts to evaluate access to maternal health care. So you perhaps have heard this, but I feel like it's a big talk recently that the US has the worst maternal mortality rate among peer nations. So this is a pretty bad look for the US, and kind of the headline reason for this is that American women are in poor health when they get pregnant and do not receive proper care during and after their pregnancy. And part of not receiving proper care is that they lack access to maternal health care, that they're traveling far distances, that they struggle with like having correct insurance and getting to their prenatal care and delivery visits. So that's what I'll be focusing on in this presentation. But with this kind of new awareness of this maternal mortality crisis is that there's increased attention and funding to help solve this issue. So you can see the U.S. Department of Health and Human Services and the National Institute of Health has really recently allocated a lot of funding to improve this situation. And so the kind of OR question becomes, how should we allocate these resources in the best way in order to get like the best outcomes using this funding? So my research is focused on which regions actually do lack access to care, and should these resources be allocated to improve access to care. And specifically what we're looking at is there's two main measures of maternity care access that are really widely used in like literature and also in the news. Like the maternity care deserts measure is released in a report every 2 years, and it makes big headlines about what states are improving or not improving in lack of access to care. So the definition of that maternity care desert measure is a county-based measure, and says if a county has no obstetric hospital and no obstetric provider, then it's a maternity care desert. And then another measure that is widely used and that we compare it to in this work is a distance-based measure that says if you're further than 50 miles from critical care, which is the highest level of care, level 3 care, then you don't have access to care. So we're looking at these two measures and kind of the implications of allocating resources according to these measures. So here's what measures actually look like in my home state of Georgia. So you can see that these maps look very different. So on the left, we have maternity care deserts. Again, this is a county-based measure, so it's more granular. And so there's kind of like areas that are deserts surrounded by places that aren't deserts, and places that aren't deserts surrounded by places that aren't deserts. So very granular measure. And then if we move to the further than 50 miles from critical care measure, you can see this is much less granular, and kind of gives you this like large region in the southeast that lacks care in Georgia. So we kind of thought like if someone was given these two maps, it would be hard to kind of know like where should we focus our energy, where should we put new hospitals, put new providers, and like what's the value of these different measures if we actually want to improve them. So our research question was, what facility expansion policies do these access measures imply? And to do that, we formulated mixed integer programs to allocate new or upgraded facilities to maximize access according to each of these measures. So we use very simple facility location mixed integer optimization models to do this, with the objective function just being the access measure we want to minimize. So again, we start with these two maps that I showed in the previous slide, where we have maternity care deserts and regions that are further than 50 miles from critical care. And the stars are existing hospitals that count as access according to these two measures. So first, if we want to improve access by 50%, to do that under the maternity care deserts measure, we would need 16 new hospitals at least to reduce the number of women who live in maternity care deserts by 50%. Whereas if we're looking at the further than 50 miles from critical care measure, we only need 2 hospital upgrades to reduce the number of people who lack access by 50%. And you can see the blue stars are the new or upgraded hospitals. And then finally, we want everyone in Georgia to have full access. According to the maternity care deserts, we need at least 56 new obstetric hospitals. Whereas in the further from 50 miles from critical care, we need just at least 8 hospitals. So the kind of main conclusion from this is that these two measures inform very different strategies for improving access to care. And it's kind of hard to say like which of these should we use. Do we need tons and tons of new hospitals? Do we only need a couple? And we really wanted to highlight that these existing maternity care access measures have significant limitations. So for the further than 50 miles from critical care, this only considers the most specialized care. So like the most specialized, very like high level care, and most women don't need that high level of care. Most women are fine with very standard levels of care. So this is only kind of considering a small part of the population in this critical care obstetric measure. The maternity care desert measure, I think, has some more limitations. So for one thing, it's a county-based measure. And counties in the US are not standardized in size, shape, anything. There's very high variability between states. Georgia has the second most number of counties of any state, even though it's not a very large state. Only behind Texas has more counties. And in Georgia, 82% of people who live in maternity care deserts actually live within 25 miles of an obstetric unit. So it's hard to say if this is really capturing lack of access to care. And then it also doesn't consider the quality of obstetric facilities. So you could, if every county had like one very low level, poor quality, poor performing hospital, then we could say Georgia has full access to care under this measure, where that maybe doesn't actually capture high quality, accessible care. So to conclude my presentation, we really wanted to focus on like this maternity care desert measure that is really highly publicized and highly talked about, is perhaps not the best for actually thinking about facility expansion and improving lack of access to care. So for example, like I mentioned before, we need 56 new hospitals in Georgia in order to eliminate maternity care deserts. But introducing this many facilities might actually have negative consequences. So for one, this would dramatically increase the amount of workforce required in Georgia, and would dilute volume across facilities. And it's been shown that facilities with not very many births occurring in them every year, they have worse outcomes. And so it might be better to consolidate care in fewer facilities rather than to kind of flood a region with a lot of facilities. And also in Georgia, facilities are closing currently. There's been 33 closures in the last 30 years. Hospitals are not opening. So this solution is really not feasible and also maybe not even helpful. So thinking about improving access to care according to maternity care deserts may actually worsen maternal health outcomes in Georgia. So in this paper that we've recently published in BFC Health Services, we conclude that we need more robust ways to evaluate and track progress of improvements to accessible, risk-appropriate care. Thank you so much, and I can take any questions if I have time.
Thank you, Megan. We do have time for one or maybe two questions.
I got a question.
Great.
Yeah, so I was wondering, could you give us more insight on like the model? I know you mentioned that it was a mixed integer program. Like what were like the details on like the constraints and how difficult the model was to solve and stuff like that?
Yeah, it was a really simple facility location model. So the objective was like minimize the number of people who lack access according to this measure. And then we just kind of say like every, we want to locate facilities. So I think, yeah, like extremely simple model to start to run.
Cool, yeah. Thanks.
Yeah, thank you.
Good talk by the way. Great.
Yeah.
Carmen, you raised your hand. I think you're allowed to unmute yourself now if you want to ask your question.
Okay. Just really quick, did you think about factoring in like population factors, like socioeconomic factors of people in those regions? As you said, like counties are not very uniform. So are there any other metrics or things that you wanted to factor into your model other than just location?
Sorry, I didn't hear the question. That's fine. What? Could you repeat it?
I'm just gonna write it in the Q&A, okay?
Okay, sorry.
Thank you. Thank you for the questions. Thank you, Megan. And we are ready for our next speaker. We welcome Sekai Wang.
Thanks. Let me share my screen. Can you see my screen?
Yes.
Okay, cool. Good morning, everyone. My name is Sekai Wang, and I just graduated from the University of Tennessee, Knoxville. Today, I'm very happy to talk about my recent research, the MuseNet, the missiness over multi-branching self-attention encoder for irregular longitudinal electric health records. So first, I will briefly talk about the motivation and the background information of this research. So nowadays, due to the advanced sensing and information technology, we currently live in a data-rich environment. For example, in the healthcare domain, there are a lot of the electronic health records, also known as the EHR data, accessible and available. So typically, the EHR data is the digital version of the patient history, which includes the many different data types, such as the demographics data, the vital sign, the diagnosis, waveform data, and also the laboratory test. It gives us a very good opportunity to develop a reliable data-driven decision prediction method based on the EHR dataset. One important subtype of the EHR data is the irregular longitudinal EHRs. So this flowchart summarizes why we have the irregular longitudinal data in the EHR systems. Specifically, a patient usually have the multiple clinical encounters over time, and within each clinical encounters, the healthcare provider will assign some laboratory some diagnosis code will be assigned to this patient by the healthcare providers based on the clinical evidence and also the reasoning. After that, some laboratory tests will assign to these patients, and the result of those laboratory tests will directly stored in the EHR systems. If we collect all the laboratory test result for this patient over time, we can get the irregular longitudinal data, as you can see on the right-hand side table. This is a very complex data structures because first, it has an irregular sample, the multivariate time series. Usually, the multivariate time series has an intra-sequence correlation, which is the correlation within one time series sequence. It also has an inter-sequence correlation, which means that there are some correlations between the different time series data. This is a complex correlations and require a robust method to handle that and to find the patterns from the multivariate time series. Another problem is the irregularities. As you can see in the table and also the scat plot, for each time series features, the time interval between the different time steps are not consistent, and which make the traditional time series analysis method not work. So we also need a robust and efficient method to handle such irregularities in the time series data. Another common issues in the EHR system is called the considerable missing values. This is a very common issue in the healthcare domain. The missing values is usually because of the heterogeneity in the clinical needs and also the lack of the documentation. As you can see at the bottom, this bar chart summarizes the missing value rate for all features used in our diabetic retinopathy dataset. You can see all the time series features has missing values, and some of them has a missing value rate even greater than the 60% or even the 70%. If we left these problems unaddressed, it will cause the loss of information and also will introduce a biased estimate for us if we use that model, or if we use that data set to build a model. The last problems which is also common in the EHR systems is called the extremely imbalanced issue. We usually formulate the disease prediction problem as the binary classification problems, which usually in this pie chart shows very common scenarios in the healthcare domain, which the negative samples, that means the patients without some specific conditions, usually consist of the majority in the data set. It will give us a very skilled performance if we left these problems unaddressed when we build our deep learning or machine learning models. That means we will have the very good performance on the negative samples, but have a really bad performance on the positive samples. However, in the real world, usually the minority of the positive samples or class is more important in the disease prediction problems. Because of those challenges, we proposed our own method, the MUSENet, the missiness-aware multi-branching self-attention encoder network to handle those challenges. I won't talk about the details of these models, but I would like to mention 3 key modules in the model. The first, we use the multitask Gaussian process to handle the missing value imputation for the multivariate time series data. We also proposed a mismatch-aware self-attention encoder, which can efficiently handle the irregular multivariate time series in the EHR systems. At the end, we proposed a multi-branching layer, which not only can handle the imbalanced issue, but also can improve the training procedures and make the training procedures more efficient. To test our model performance, we use two datasets. The first one is the syntactic dataset, which generated by the autoregressive moving average models, which consist of the 5,000 samples with 90% from the majority class. We also test our models in the real-world dataset, which related to the diabetic retinopathy. And this dataset is from the Cigna Healthcare Factors Data Warehouse, which consists of the 21 blood tests, the 5 comorbidity indicators, and 3 demographic variables, and 1 variables evaluated the duration of these patients. This dataset consists of more than 20,000 diabetic patients, with only 9% of the diabetic retinopathy patients. We use 2 evaluation metrics in our research. The first one is the ROC curve, which evaluated the false positive rate and the true positive rate. And the summary statistics is the area under the ROC curve, which evaluates the overall performance for all the benchmarks and our proposed framework. Similarly, we also use a precision recall curve, and it evaluated the relationship between the recall and the precision under the different threshold. And the overall statistics is the area under the PR curve. Let's see some main result in our research. This plot shows the ROC and AOPRC scores across the different epochs for our proposed MuseNet, using the different imputation method on the validation data set for the synthetic data. As you can see, our proposed method, the multitask Gaussian process, has a very good performance in both the AOROC, AOPRC curve, and also the convergence speed. It demonstrated that it can capture the both variable interactions and also the temporal correlations in the irregular sampled multivariate time series. Again, this table summarizes our model performance and also some benchmark performance in the real-world diabetic retinopathy dataset in the test dataset. Specifically, the table 1 shows the MuseNet, our proposed model, and the other benchmarks. The second table shows the MuseNet with the multitask Gaussian process imputation and other imputation method. And third one shows the model performance under the different multi-branching numbers in our framework. All the tables shows our proposed model has the best performance, which achieved the AOROC score 0.9, almost 0.95, and also the 0.883 AOPRC scores. This table shows the performance. This table shows the performance improvement because first we use the mismatch-aware self-attention encoder, which can efficiently handle the time series, the pattern to capture the patterns in the time series data. And the multitask Gaussian process imputation can also efficiently impute the missing values in our dataset, and the multi-branching layers can also efficiently prevent the imbalanced issues in the EHR dataset. To conclude my research, we proposed a novel MuseNet framework for the reliable automated diagnostics. We use the multitask Gaussian process and the missing value masks to capture the multidimensional mismatch patterns in the EHR dataset. And we also proposed a time-aware self-attention encoder to model the irregular longitudinal EHR data. And finally, the multi-branching architectures can efficiently handle the imbalanced issue. This framework has a very broad applications. It can handle the general multivariate time series classification with the irregularities, missingness, and the imbalanced issues. We have already employed this framework to investigate the different data set in our to investigate the different data type in the EHR systems, and got some publications in the journal. This research is under the first round review at the Informs Journal of the Data Science, and this research also based on my previous research, which has already published in some top-tier journals such as the IEEE Journal of the Biomedical and Healthcare Informatics. That's it. Thanks for your attention, and feel free to reach out to me if you are interested in more details, and I'm happy to answer any questions if I have time.
Thank you for your presentation. We do not have time for extra questions, but if you want to ask in the chat, we can welcome questions in the chat as well. So
Okay.
we are ready for our next speaker, Yanan Xu.
Oh, can you see my screen?
Yes.
Okay, that's great. Okay, good morning, everyone. Today I'm going to talk about our research project, Personalized Assortment Optimization for Subscription Business Model, which is a joint work with Professor Gai Ban from Imperial College London, Professor Weda Amgrabi from UMD, and Professor Bel Tokte from Georgia Tech. So here's our motivation for this study. Fast fashion has already revolutionized the entire apparel industry, bringing the latest trends from the runway to your closet at a breakneck speed. However, this comes at a huge cost. The fashion industry is now the second largest polluter globally, just after the oil industry. And it's clear that our current clothing system doesn't function very well. A natural question to ask is how we can utilize more sustainable business models. One potential remedy is a clothing rental subscription model. We observe so many startups embrace these new business models in the past few years, and some of them have made the company to public. On high level, rental subscription models can provide customers with access to a variety of clothes while decreasing the demand for new clothing production. However, here's the reality from company we collaborate with. Based on the survival analysis, we found that the median survival time for customer on monthly subscription plan is just around 61 days. So it's just 2 months. Companies are now struggling to convince people to make monthly payments for rented clothes, with many of their consumers complaining about the recommended assortment didn't match their styles and needs. So what kind of firms do with this customer dropping off challenge? One decision they have in control is the assortment. In other words, what they recommend to the customers. Suppose the inventory has already been procured, then the firm's problem is just to choose a subset of items from the product universe under the big K cardinality constraint. And then after observing the personalized assortment ST based on customers' evaluation of the items, they then either choose a particular set of items to fill in their shopping basket under the subscription plan constraint or do not subscribe. So for instance, a customer who is active under a monthly 4-item subscription plan would choose 4 garments to fill the basket. Conversely, if the customer doesn't find the assortment appealing, they would not subscribe. And specifically, we investigated further about the reasons why they cancel subscription plans, and the majority of customers are complaining about the difficulty to find suitable items that fits them well. So as a result, it's worthwhile to consider this product fit uncertainty when designing a personalized assortment, and thus here comes our research question. How should a subscription company make assortment personalization considering the product fit uncertainty problem and maximize expected lifetime revenue from a customer? Here are 2 streams of literature related to our research project, basically assortment optimization and subscription business models. Our paper is related to a rising stream of literature in assortment optimization at the operational level, considering the presence of multi-item. And in this project, we investigate a doubly combinatorial assortment optimization problem and incorporate the product fit uncertainty into a subscription decision model. So here's our model. Let's take a look at customer decision process first. When the new customer tier arrives, they need to fill out a survey and thus reveal customer feature information, such as customer preferences, body measurements, and demographic information denoted by customer feature ZT. After observing customer features, the form then recommends a personalized assortment under the cardinality constraint BK. Upon observing the recommended set, the customer derives ex-ante utility based on the items they would like to try on and then compare it with the discounted plan price. If the ex-ante utility is higher than the threshold, then the customer will subscribe to the plan. Otherwise, they will say no to the company and do not subscribe and just walk away. Suppose their decision is yes, then the customer would order a subset of products from the recommended assortment under the subscription plan size constraint small m. After the customer gets the clothes and tries them on, they then derive ex-post utility from the ordered item and makes the subscription renewal decision based on the value of the ex-post utility and the normal subscription plan price. So finally, the customer would renew the plan if the ex-post utility is larger than that threshold. Then for the demand model, we assume customers derive a utility based on two parts, the ex-ante part colored in red and ex-post part highlighted in blue. Well, we assume both the ex-ante and ex-post random shocks follow multivariate normal distribution, and the ex-post random shocks capture the product fit uncertainty. We assume epsilon j is independent of gamma j for all of the products, and product 0 just denotes the non-subscription alternative. Then for the first problem, we can define the expected profit function as follows. Well, the first part is just the expected profit in the first subscription period, which is a product of the profit margin under a discounted plan price and the initial subscription probability. And the second part is just expected profit from subscription renewals, which is a product of customer lifetime value and subscription renewal probability. And the problem is very difficult because of the probabilistic terms in the objective function. So without smart theory, we have to do brute force calculations. Specifically, we'll just do it by Monte Carlo simulations, which is computationally very demanding. So in order to tackle this problem, we first introduce the bounds for the initial subscription probability. And you can observe like both of the lower bounds, upper bounds, they are functions of signal to noise ratio. And I will elaborate more in the following slides. So we can establish the lower bound, upper bound for the second probabilistic terms in the objective function, which is just the probability of continuous subscription. So assume we have independent random shocks, then we can achieve pretty good analytical results for two extreme cases. Well, the M is equal to 1, when the subscription size, basket size is equal to 1, or M is equal to BK, when the subscription size is just equal to the cardinality constraint. In other words, the customer will just passively receiving the items recommended by the company. So to summarize, the lower bound is exact for both probabilities when M is equal to BK, and the upper bound of initial subscription probability is exact when M is equal to 1 and M is equal to BK. So motivated by our analytical results, we can now tackle the problem. So we first consider a special case where the basket size is said to be 1. So when M is equal to 1, we can solve the following problem by replacing the probabilities with their upper bounds. And here we introduce several rotations to simplify the representation of the original probability. So we define the ex-ante signal-to-noise ratio and ex-post signal-to-noise ratio respectively, and use C1 and C2 as the parameters in front of these functions defined in the objective function. So we can first just divide our original objective function by C1 plus C2 and take the logarithm of it. And we can further exploit the concavity of the logarithm function and come up with a very clever analytical approximation. So we can just solve the problem approximately by taking a simple ranking problem where it's just about computing this function of ex-ante and ex-post signal-to-noise ratios. So for a more general case, we propose a similar algorithm to find the near optimal assortment by computing the weighted logarithm values for subsets and rank them in ascending order. So then we can just select the bottom, the floor function of K divided by M subsets, and then randomly choose other items from the lag subset to meet the capacity constraint BK. So in terms of the performance of our algorithms, we demonstrate that our heuristics actually give you amazing results. You will be within 6% of the optimality gap and takes much less time to solve. And here are managerial insights from this project. So on high level, the composition of the optimal assortment can vary significantly depending on customer type. And specifically, we formulate 3 different regions where the company needs to implement different strategies towards different customers. So on high level, the key message is that if you see a keen customer, don't take risks. Just show them the safe items. But if you see a customer who doesn't seem keen, you need to show them with high variance items. In other words, you need to present them with very different items with very different styles and can sometimes surprise the customer and entice them to join the platform. So to wrap it up, here are a few key takeaways from this talk. We tackle a combinatorial assortment optimization problem for subscription business model, and specifically by incorporating the product fit uncertainty into this model. We propose efficient, generalizable, and trackable algorithms with provable optimality gaps. And finally, we categorize the optimal assortment structures and derive insights on how subscription service providers can optimize their assortments. Thank you for your attention. I'll now open the floor for any questions you may have.
Thank you, Yanan. We do not have time for extra questions, but again, I welcome everyone to ask them, post them in the chat. And we have now our last speaker of the day, Shihan.
Okay. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Zihan Zhang from Georgia Tech. Today, I will present our work, Federative Multiple Tensor Regression for Multimodal Data under Data Sharing Constraints. In reality, we will handle data in different formats. For example, we have the process settings as scalars, and we also have the sensor readings, such as the profile data, and we also have like the image and video signals as the streaming signals. Due to the advancement of sensing technologies, nowadays we have the high sampling frequency sensors, high resolution cameras. All this signal collection will help us to get the structured high dimensional data. Regarding the real problems, when we consider a hospital, we will measure different types of the indicators to represent the patient's health condition. Then our problem is how we can evaluate the health condition of a patient based on the multimodal data. Especially if we have multiple hospitals, how can we handle such problem? Considering the agriculture, we also need to evaluate the growth conditions of plants based on the multimodal data, such as the temperature, humidity. And when we have multiple sites, how can we still evaluate the growth condition based on the historical data? As we can see from the motivating examples, there are several distributed sites involved, which will result in the distributed high-dimensional multimodal data. If we want to build up a predictive model, if we only utilize the data from the local sites, we will have limited data, which means we will have the poor data generalization capability. But if we pulling all data to a global server, it will require us to directly share all the data, which may violate the regulation policies. And it also hard for us to design a personalized model for the local sites. When we transit such data, it will also result in the huge cost regarding the storage and transmission. Thus, our research question is that, how can we model the structured high-dimensional multimodal distributed data without direct data sharing and reducing the modeling costs? First, let's consider how we can handle the first challenge regarding the structured high-dimensional data. Here we consider to utilize tensor to represent our data. Tensor is a multi-dimensional array. Vector can be represented as a 1D tensor, and also we can represent a matrix and the cube as a higher dimensional tensor. And we also can structure the historical data as a tensor as follows, such as the functional curves and the streaming image. They can also be represented as tensors. For the second challenge, multimodal, in order to handle multimodal data, we resort to the multiple tensor regression proposed by Mustafa Raisi. Here we consider we have a training data, and for the training data for the input, we have the different types of the input, and we also have a high dimensional response. We want to build up a predict model based on the training data and apply the regression model towards the new data to predict the response. In order to handle both 1 and 2, like the structured high dimensional model data, we will build up the predict model for each local site. By using the tensor decomposition, we will extract the low dimensional features from the high dimensional coefficient. And we will store such coefficients to our local database to handle the structured high dimensional model data. So our next challenge is how we can handle the distributed data. In order to address this challenge, we proposed our federative regression framework. Specifically, we have an aggregator to coordinate with local sites to build up an aggregated model at the aggregate level. And for each local site, we will build up the personalized models by communicating the data features with the aggregator. Specifically, we proposed a two-step algorithm to learn the model coefficients B here. Specifically, for the input basis U, we will learn from the input data based on the communication among the aggregator and local sites. Then we will study the co-tensor and output basis from the correlation among the input and output. And this will be our second stage. Regarding the first stage, we will learn the input basis. This is our master problem. Here we assume that we have access to all the data. The first term will help us to learn the input basis from the input data X. And the second term will help us to reduce the potential decomposition result by when we learn the input basis. Here we assume that given a specific data type K, all the data will come from the same distribution. However, in the reality, we don't have the access to all the data together due to the data sharing restrictions. Hence, we decompose our master problem into two sub-optimization problems. At the aggregator, we will have the aggregated optimization, and for the local sites, we will solve the site-specific optimization. Between these two levels, we will transmit the data features instead of the raw data. Regarding the site-specific optimization, we will have the linearly decomposed optimization. For each local site, we will learn the input basis from the local input data X. And based on the data sharing constraint here, we can communicate the data features among the aggregator and local sites. Regarding the aggregated optimization, it will handle the orthogonality penalty term. And based on the data sharing constraint, we will enable the data sharing. To have an overview, firstly, we will have the local update. All the local features will be transmitted to the aggregator. Then we will have the global update. The aggregator will update the global features and send back to the local sites. By communicating among the aggregator and the local sites, we will reach consensus by satisfying this constraint. Then let's talk about the second stage. We will learn the co-tensor and output basis. In our optimization problem, we will first learn the model coefficients based on the relationship between the input and output. For our second term, it will also help us to reduce the potential decomposition results when we learn the output basis. And for our last two terms, it will allow us to have a deviation of the local features from the global features. Based on our constraint, we can learn our model coefficients B by decomposing it to input, output, and co-tensor. However, in reality, we still don't have the access to all the data due to the data sharing constraints. In a similar way, we will decompose the master problem into aggregated optimization and the site-specific optimization. Due to time limit, I will not discuss more details regarding the optimization problem here. Now let's talk about our numerical studies. For the benchmarks, we consider 3 types of methods. The first method is a global model, which means we will utilize the data from all local sites to train the regression problem. Regarding the local model, which means we will only use the local data to train the regression problem. And for the third method is called the federative average method. It's a popular federative learning method. Under our proposed federative framework, we have 2 types of the methods. The first method is called the post-personalized model, which means when our proposed algorithm converges, we will run an additional site optimization to personalize our local models. And our second type of federative model is called the aggregated model. For such model, when we will first run our algorithm, when the algorithm reaches the consensus or the converge, we will construct the aggregated model based on the aggregated features from the global level. In our case study, we consider the estimation of the lambda profile. Specifically, when we consider the combustion of the vehicle, we have multiple sensors to monitor the condition of the combustion, and we want to predict the lambda profile, which will be an important indicator for us to evaluate whether the combustion is under a good condition. Specifically, we will split our data into the training and testing data sets. And here we consider we have two vehicles, and we will evaluate our model performance based on the standard prediction mean and squared value. And based on our numerical results, we can find that our proposed federative methods achieves a good performance, especially compared with the local model. We can significantly improve the prediction performance. To summarize this work, we proposed a federative multiple tensor regression. By handling the multimodal structured high-dimensional data, and based on our framework, we can protect the data sharing regulation policies, as well as reducing the storage, computation, and communication cost, because we only handle the low-dimensional features instead of the high-dimensional data. Regarding the theoretical contribution, our proposed model is a generalization of the traditional regression model for the distributed sites. And since we can handle the data from multiple sites, it can help us to improve the capability regarding the scalability and the model and the efficiency when we handle them a large amount of data. Regarding the application, our proposed methods advance the data analytics in diverse fields. Apart from the vehicle combustion, we can also apply our methods to healthcare and agriculture. And also, and besides, since we introduce the equality constraint, it will also help us to promote the fairness when we consider the real application. This is the end of my presentation. I'm happy to take any questions if you have. Thank you.
Thank you, Jehan. One more time, we are just at the end of our presentation, and there's no time for additional questions. I just wanted to thank all of our speakers from today's session and from the previous session. With these 2 sessions, we conclude the competition. I invite you all to scan the QR code and vote for your favorite session for today. And also to conclude our summer series, we will have another session that is going to happen 2 weeks from now. It's going to be a senior researcher webinar where we are going to have Mark Lewis from Cornell and Charles Worrell from MITRE present some of their research. So keep an eye on the registration link, which we will be sharing with everyone very soon. And so with that, thank you all. Thanks again to our speakers. Thanks to our judges and for everyone who attended our sessions. And we'll see you 2 weeks from now in our Senior Researcher webinar. Thank you. Have a good one.